Hey, new project day today. You may remember in a previous video where I made this 10 megahertz oven controlled crystal oscillator frequency reference. Nice bit of kit, works quite well, except when I don't need 10 megahertz, then it's not so useful anymore. Sometimes I need to calibrate a piece of equipment with a frequency other than 10 megahertz. There is some equipment that needs 5 megahertz or 1 megahertz or whatnot, and this doesn't really cut it because it's only 10 megahertz. So I thought, hey, maybe I'll make a module that I can plug into this using the same case so it all matches. That will let me divide that frequency down. I have a switch on the front that lets me choose from preset frequencies, and it will help me to then calibrate the equipment that needs something other than 10 megahertz. So PCBWay actually contacted me and said, hey, let's work together. So I said, sure thing, and they sponsored this video with some PCBs. So let's have a look at what they sent. Not looking too bad at all. They got the usual 5 PCBs that you get from the online prototyping services. And yeah, let's have a bit of a closer look. I'll zoom in a bit and we'll have a look at the quality of these PCBs. So here we got the top of the board. Nice consistent solder mask. Silk screen's nice and crisp. It all looks pretty high resolution, or yeah, definitely not the old dot matrix cheap way of doing it. Plating is nice and shiny. There's a back there. Not a problem at all. Thumbs up to PCBWay. If you want to check out their services, you'll find a link in the description below. But that is good. I'm happy with that for my sample size of 5. No complaints at all. So let's head over to the computer and I'll explain how this circuit's going to work. So here we are with the schematic mostly done. I'm sure I'm going to tweak a little bit here and there, so I'll say it's 99% done. This is just in my my PCB layout software of choice, DipTrace. So let's start from the top and work our way down. So over here in the top left hand corner we've got our power LED, green LED, none of this blue rubbish, and a resistor which I'm going to test empirically. Once I've got the circuit boards made, I'll just try a few different resistor values to get the right brightness. I don't want it too bright that's blasting my face, but I want it bright enough to see on the bench, so I'll just set that till it's just right. Then all of these things, these little blocks of stuff, these are just the voltage in and the ground pins on each TTL chip. That's just how it's represented in the schematic here, and we've got some bypass caps, 1 per TTL chip as is convention, just to smooth off the ripple and give a little boost of power once each time the chip switches, the transistor inside switch, they gulp a little bit of power, so that capacitor just fills in to make sure that we get nice clean transitions and whatnot. Standard stuff for TTL. And then over here we've got 2 10 microfarad capacitors. That's just a bulk supply capacitor, just to stiffen up the supply, bit of filtering, and to make sure we got no supply sag, no ripple sag, or any other problems with the power supply. And of course here is the 5 volts input. That's just going to be a little header on the PCB, and that's going to break out from the PCB to a rear DC input jack. And because I'm going to be taking the 10 megahertz from my 10 megahertz reference, which I featured in a previous video, I'll probably put a 5 volt output jack on the back of that. I'll just modify that in. So I'm taking 10 megahertz from the 10 megahertz reference, and I've got a good 5 volt power supply in there, so I may as well take 5 volts too to make it all neat. That way I'm not having multiple power connections. I'll just have one connection into the 10 megahertz, and everything loops over to this frequency divider module. So here's the main part of the circuit. We've got our 10 megahertz input over here, and that's got another header pin which is going to break out to a front BNC input jack. That will then connect to the BNC output jack on my 10 megahertz reference. We'll come across to this C11. I'll just zoom in a bit here. That's a 1 nanofarad. I've just put that as a ballpark figure. That's just an AC decoupling cap, just to stop any DC bias coming in and also DC bias coming out, because I've got this DC bias resistor here, R1. It's a 10K trim pot. That's just to set any bias that's needed to make sure that the TTL over here starts switching properly, just in case, just to take into account any funny business with the 10 megahertz coming in. We come into this buffer here. It's a 74LS14, yep, standard buffer. That's just amplifying the current, so that if the input waveform is a little bit weak, like the voltage or current or whatever the supply is a bit weak, this here just boosts it up a bit to make sure that it's capable of driving all the TTL that it has to. Because that comes up to this buffer here, it comes to this chip and to this chip here. These These two squares are one 74HC390, one counter chip, and then we got a second one here in shown as two modules, and then a third one, and so on and so forth. So you can follow the line from pin 2 just here, comes along into pin 1, and loops around down here and across to pin 12 and up to pin 3. So we're driving 3, so I just want to make sure that we're able to drive that correctly. And of course all of the outputs are also on buffers, just to make sure we're kicking out a reasonable amount of signal to make sure that's going to drive whatever we're plugging this test unit into, the device under test. So this here, the U2.1, that's a divide by 2. So we go from 10 megahertz down to 5 megahertz, and then that's all that does. That doesn't loop on anywhere. This one here is the other half of this chip, and you can see there's some pins going nowhere. It's tied down to ground. I've done that so that all the inputs are tied to ground, so the thing isn't going to be flapping in the breeze and oscillating with transient just hash and junk, because they can tend to do that, and that can cause some problems, like it can cause interference and whatnot. So by tying the inputs down to ground, it effectively disables this part of the chip, and it won't have any effect on the rest of the circuit at all. No oscillations, no buzzing around with interference. I've done the same here. The first buffer chip, because I've got two 7414s, and the first one I'm not using 2 gates, so I've tied those down to ground just to be safe as well. Just a bit of housekeeping, bit of good practice. So the signal, the 10 megahertz, it comes into this divide by 2, but also it comes around, as I said before, to pin 12 here, into this one here, which is divide by 10, which takes the 10 megahertz down to 1 megahertz through that buffer and out here. Then it loops around down through here to pin 4, and that's another divide by 10, which gives us 100 kilohertz, and then again 10 kilohertz, and then again 1 kilohertz, 100 hertz, 10 hertz, and 1 hertz, 1 pps, 1 pulse per second. So that's given me the whole range from 10 megahertz all the way down to 1 hertz, like all the decade values, plus 5 megahertz there. So these all break out off the PCB on this header pin J4. That's just going to be going to a rotary switch, and that will let me select which output frequency I want, and then it loops around out of the con here up to this header pin, which is going to go out to the output BNC jack, frequency output. That way I can just plug my 10 megahertz in, plug my device under test to the frequency output, and then just dial in what frequency I want. I don't envision I'm going to need multiple frequencies at once, and so I may as well just have a switch just to simplify the front panel, so I don't have a forest of BNC connectors, because they're a little bit, they cost a couple of bucks each, times by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It could be like 20, 30 bucks worth of BNC jacks, and I don't want to spend that much money. It's cheaper just to put a switch, and cheaper and neater to put a switch, one BNC input, one BNC output, we're done. So that's the schematic, basically somewhat described, clear as mud. So the next step, I'm not going to put this onto a PCB just yet. I think I might go and grab a breadboard just to try at least a portion of this circuit, the first 1 or 2 stages, just to make sure that I've got things right, that it's going to work, and I've got the concept down. So we've got a 10 megahertz reference here. This is the subject of a previous video, which you can check back, a relatively recent one. So 10 megahertz is coming out of here, coming around into here, through the little DC blocking cap, the little AC coupling cap, and there's a bias pot there as in the schematic. That then comes through the buffer and then into our counter chips. So the first one here, we've got the, it's all like a bit of a mess of wires, but it's wired as per the schematic. That then comes back through the buffer chip, the 7414, and then out to the scope. I didn't bother doing these ones. All these green wires are the outputs. I didn't bother doing these through the buffer chip just to simplify things, and I'll do one, make sure the concept works, and then the rest I'll just measure directly out of the counter chip. So at the moment we've got it hooked up to the 5 megahertz output. And on screen you can see there, it looks a bit messy because it's a breadboard and it's not optimized at all for the higher frequency or whatever, the 5 megahertz. So we are getting 5 megahertz, which is fantastic. A somewhat square wave. Capacitance inductance of the breadboard is throwing that off, but let's move it to the next one. I believe this one here, we're getting 1 megahertz. And then if I go to the next one, and that is 100 kilohertz. And then if we come to the next one, 10 kilohertz. And the next one, the last one I've bothered connecting, is 1 kilohertz. Fantastic. I could go further down to 1 hertz, but if a few of them work, the rest of them are going to work the same anyway, because it's all just carbon copies of each module. Like each chip is just like a module that I just carbon copy on the schematics. Basically, the concept works. Time to start construction. Don't worry, this isn't the SD safe workstation. I'll turn on the soldering iron. Time to hit the time lapse. And there's our board, all soldered up. Beautiful. I'll clean the flux off later, but that is looking quite nice. So that's ready to go in the enclosure for a test fit. I've got a Takachi brand, HEN 110412B, B for black. So let's open this one up. It's just the same as the 10 megahertz reference. I think I bought the same one. Yes, I did. Excellent. And that should just slide. If I get the right slot, straight in there, like that. Beautiful. Oops, got the LED a little bit bent. Nice, that's going to be good. That is perfect length. Like, perfect length. I like it. I like it a lot. So, the next step, I guess, is to start cutting holes in the front and rear panels. So, I've got to put one hole in the back for the power in. And then in the front, we're going to have our two BNCs. That's going to be wired to some little plugs along with the power, which will plug on to the connectors there. And they will sit somewhere on the front. I'll have to figure out exactly where, because we also have to put the rotary switch. And that will go on the front to select our frequency. And I've got a nice, it came with like a plastic knob, but that's a little bit blare, so I went and bought a nice anodized black knob. If I can get the packet open. Oh yeah. Sato, S-A-T-O, Sato parts, Japan. And that will go on there and look quite nice on the front panel. So I'll design up the front, get the holes drilled, and we'll start mounting these parts. So I've got the front panel design here. I drew up in my CAD package of choice, Rhinoceros 3D. I've just been using it for decades. So that will get cut out, and I'll put it on top of this. Then I can use the old punch to boom, 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 mark the centers there. Then I can drill it out, and it'll come out pretty much perfect. So I'm going to have the power LED there, input BNC, output BNC, and then the dial in the middle. Kind of like that sort of thing. And we're done. Pretty much finished. So that's the front panel all finished. The jacks are in there and the knob. Nice action there with the labels. Just use a label maker to make those labels. Matches the 10 megahertz reference. One day I'll have a CNC engraver or CNC mill to engrave those the labels in, but for now that'll do. The jack in the back there, mini XLR, and the same on the back of this one. You see there's a nut on there. When I first designed this, I never intended to put a plug on, so there's very little space, so I had to literally space it out the width of that nut, and that gave me just enough space to fit it in there. That's fine, it works. You'll see here, we've got the jacks there with some, these are just coax cables, like just standard, nothing too special, just like audio coax, because we're not much above audio frequencies, up to 10 megahertz. But yeah, that's fine for our uses. And all the wires going around to the plugs from the switch. Now, one thing I had to do, because I was designing this at 3 in the morning, and I made a bit of a mistake, was I didn't take into account the size of the switch compared to where the PCB sits in the case, and I had to notch the PCB out. Luckily, there's no traces there, but if I ever make this again, I'll include that notch from the when I get the PCB manufactured. Also, I might actually change the design a bit, where I'll use PCB mount BNC jacks, and I'll have a vertical bit of PCB to use a PCB mount switch, and that will then just either use some little plugs or just edge solder that PCB straight to this board to save me having to make all this loom. But it wasn't too bad anyway. For a one-off, that's fine. It works, no worries, I'm sure. So we got the power cable, which I made up with some mini XLR plugs. So they plug in the back to there. That's 5 volts out to the 5 volts in. Plugs in there nice, and it's locking, so it's nice and secure. And then I've made up a short little BNC cable. If you watch my earlier videos, there's one on how to build these BNC cables. They're Canair crimp style, and they're actually very, very good quality. So that's nice. So you can have it sitting side by side, or even on top, one on top of the other, whichever way you want to go. And that's going to sit on the bench quite nicely. So we'll put the lid on, hook it up to the scope, and see how it performs. Alright, so let's see what the output's like. I'm taking video of the screen at the moment because I can't take a video screen capture from my scope. And we're running at slow speed, so it's a bit more interesting to see the signal propagate across the screen rather than just a static screenshot for some of these. So let's turn it on and see what we get for 1 hertz. 1 hertz pulse there. You can see on the right hand side the frequency and RMS and peak to peak values and all that aren't showing up because it's so slow it can't really figure it out, but they'll come up with the higher frequency. So that's the 1 hertz setting. We'll go up to 10 hertz, and see there it's a lot, it's actually 10 times faster, a lot faster. So if we bring that up to about the same, now we can get something. So I'll switch over to screenshots now because there's not going to be anything propagating across the screen anymore. So here's a 10 hertz signal. I'm measuring these at DC coupling, by the way, not AC coupling, because long period times it tends to, like the internal capacitor of the scope tends to round off the signals, so they end up like spikes rather than nice square wave, because the capacitor ends up blocking the DC, which is the top part of the waveform. That's just a measurement thing. So 10 hertz looks pretty good. It's exactly 10 hertz. Let's head over to 100 hertz. That's exactly 100 hertz. Looking good. It's going to be pretty much the same thing over and over. 1 kilohertz. Yep, we got 1 kilohertz as well. Looking pretty alright. 10 kilohertz. Yep, still looking like a 10 kilohertz square wave. 100 kilohertz. Yep. 1 megahertz. Still doing its thing. 5 megahertz. Now it's starting to get a little bit funny, so I'm going to zoom in a little bit more than we have before. You see it's starting to round off. That's just because of the construction of the circuit with those longer fly leads and stuff. We're getting to a higher frequency where impedances and trace lengths and stuff are getting a little bit more critical. But it's still usable, I think, for what I'm using it for. I just need an actual like 5 megahertz pulse or 5 megahertz signal of some description to reference against. I don't need purity and accuracy of the actual shape itself. And 10 megahertz. It's kind of starting to round off to the point. It's looking a little bit more sine wave, but once again, for using as a reference, that's fine. If I need 10 megahertz to be pure, like a pure sine wave, I'll just go back to the source reference and use that itself. So yeah, but that's fine for just a frequency reference. You can see the scope is picking up 10 megahertz, and that's basically all I need. Just some way to measure 10 megahertz itself. And with that, we're done. All working. Fantastic. So thumbs up to PCBWay for supplying the PCBs, and thumbs up to me for making something that works. Awesome. Hope you found that interesting. We'll have some more videos soon in the future, so stick around and we'll see you then.